Awesome. Hey, everybody. Sorry about that. We were having some technical difficulties on our end. But welcome to our second pre-briefing for the 2018 RASC-AL Special Edition Mars Ice Challenge. We're so excited to be here today. My name is Stacy Dees, and I am the National Outreach Manager for the National Institute of Aerospace. And in that role, I have the distinct pleasure of serving as the RASC-AL Program Manager. And before we get into introducing today's speaker, which is going to be awesome, there are a couple of other introductions that I'd like to make. So first, we have from NASA's Langley Research Center in Hampton, Virginia, is Victoria O'Leary, who is our RASC-AL Program Specialist. And she's also joined by Ania Cotton, our brand new RASC-AL Program Assistant. From Washington, D.C., NASA headquarters, we have Rick Davis. And actually, I just found out, I think he's actually in Houston today, but normally sits in Washington, D.C. And Rick is actually the reason that we're here today. He suggested doing these pre-briefs for all of the students. He's a sponsor of the Mars Ice Challenge from NASA's Science Mission Directorate, and he's actually one of the biggest champions that we have for the challenge. Rick serves as the Assistant Director for Science and Exploration, and welcome. Hi, Rick. Also in Washington, D.C., we have Bob Collum. Bob supports a variety of programs for NASA and has graciously agreed to be our technical host for these pre-briefings. So we're eternally grateful to you, Bob. I'm going to go ahead and turn that microphone over to Bob now, and he's going to introduce our presenter. Bob?
Thanks, Stacy. Hi, everyone. Today's presenter is joining us from Honeybee Robotics in Pasadena, California. Dr. Chris Sackney's expertise includes terrestrial and extraterrestrial robotic drilling, excavation, ISRU, sample handling and processing, geotechnical systems, and sensors. Currently, he leads the Exploration Technology Group at Honeybee Robotics, focusing on developing robotic systems for unstructured and extreme environments on and off Earth. In his previous capacity as an engineer in the South African mining industry, Dr. Sackney managed numerous mining projects and production divisions. Dr. Sackney received his PhD from UC Berkeley in geotechnical engineering with an emphasis on Mars drilling, his ME from UC Berkeley in petroleum engineering, and his BSc cum laude from the University of Cape Town in mechanical engineering. He has participated in several Arctic, Antarctic, and Atacama and Greenland expeditions. Dr. Sackney has over 150 publications, over 40 NASA New Technology records, and 4 NASA Group Achievement Awards. We encourage you to ask any questions for Dr. Sackney in the live chat feature on our YouTube page, and we'll answer them during the stream. And with that, let's jump right in. Now, over to you, Chris.
Thanks so much, Bob, and thanks so much for inviting. I'm super excited to talk to you about something I'm really passionate about. And I don't want this to be sort of one-way street, so please ask questions, and I'm gonna answer them as we go. Prior to the presentation, I prepared this background just to show you how far we've done so much on the surface of Mars. Right behind me, we have so-called rock abrasion tool. This is sort of very first grinding or drilling tool that we placed on the surface of Mars. As the mission goes, they normally designed to do maybe 1 or 2 or 3 operations because there is a finite life. Well, entire MER mission has been the most successful mission to date. It's still going strong. We had Spirit and Opportunity, 2 rovers. Spirit unfortunately died a couple of years ago, but Opportunity is still going strong since 2003. The grinder was designed to do 1 grind into the rocks and capture some images. Well, right on top, you have images of Spirit. So you can see we've done close to 10 before the mission essentially ended. And Opportunity, which landed in a slightly different area on Mars, is still going strong. We've done a couple of dozens of grinds. So this is, this attests to the engineering ingenuity of all folks working on a mission. We designed something for to last for maybe a year or 2 years, and these missions just going on and on. And that's especially important in this next endeavor, which is in situ resource utilization. when we design something, we're gonna be designing to, to survive certain number of operations or number of years, number of thermal cycles. But at the back of everyone's mind is a hope that these technologies will be essentially going on and on for way more than they have been designed for. So let's move to the next slide. So there are essentially two keys, two very important points related to in situ resource utilization. Next slide. The first one is exploration. Exploration essentially tries to determine what sort of water reserves or certain reserves you have in the ground. And it's not just how much and where it is. It also means, is it really feasible to pull it out of the ground? You may find that the cost required to remove resources out of the ground is essentially way too high for what we're trying to do. So exploration not only finds water, but also determines how we're gonna remove it in an economic way. How long it's going to take, the energy is required, how big of a spacecraft or landers or rovers we need, and things like this. Once we find what's the best approach to do this, then we go into the production and processing. So we essentially implementing the path that has been laid out during the very first step. Next slide, please. Mars is extremely diverse. Mars is not, it's not a single monolithic planet. It resembles, almost like Earth. Everywhere you go, you find something different. And on Mars, there are three very, very distinct regions. You have, unfortunately, we've been to every single one of them. So we have actual data point. So right on top, we have the polar regions. That's where we see a lot of ice. Then further down, we have sort of regions where it's still cold, but you still have ice below the ground. And then further towards the equator, where Curiosity is, we have regions that do not see ice, but have something that's also very valuable to us. Okay, and I'll talk about each one of these. So let's go to the next slide. High latitudes. Next slide, please. Mars Phoenix was the very first mission that landed in the polar regions of Mars. We knew there is water, but we didn't know how deep it is. So that's why we had this very deep, we had this extremely long robotic arm to dig around 0.5 meter to meter down, because we're expecting that that's where we're going to find ice. Well, when we landed, what we found is that there is a patch of ice literally 1 inch, 2 inches below the surface. So now to dig ice, you can blow it from the surface of a little bit, maybe 1 inch or 2 inch, and dig into it. During design of this mission, what we found is that it's extremely difficult to dig ice. Ice at cryogenic temperatures is essentially harder than concrete. So this is the scoop. This is an actual, qualification model of the Mars Phoenix scoop that launched in 2007 to Mars. And this scoop was the very first man-made hardware that touched extraterrestrial ice. Sorry, someone's trying to get hold of me. What we had to do for this particular scoop is develop this drill bit right at the bottom. It's called RASP. This rasping bit essentially was digging into the icy soil and transferring sample to the back of a scoop, and then the sample was made its way to the front of the scoop, where it was dumped into the instruments. So this, for the first time in human history, we touched ice that's not found on Earth, and we found that this ice is actually very salty. It's sort of like freezing ocean, and in fact, what we found later on is that ice everywhere else is also salty. the only ice, if you think about it, on Earth that's not salty, is the ice formed from water that comes from clouds. But otherwise, everything else is very salty. And this has a significant effect on how we're going to perform ISRU. You can imagine that especially folks living in the East Coast in winter, salty ice has a very lower freezing point than natural ice, than salt-free ice. So you have these brines that can be liquid at -10, -20, even at -70 centigrade. So this was really big discovery. Next slide, please. So in summary, in the high latitudes, we have plenty of water. It's near the surface. We can't really dig into it, but we can drill, or we can do direct sublimation. I've got a slide about it. But the biggest problem in these regions is that every winter you have approximately couple of feet of snow, carbon dioxide snow falling down. So we have snow falling, ice snow, water snow falling down in the East Coast every winter. We have carbon dioxide snow falling down on Mars in the polar regions. So entire polar region is covered by snow. And if you look at the picture on the left-hand side, on the left-hand side is a picture of a Phoenix lander in 2008 when it landed. So you have a big circle in the middle and two circles on the side, which are the solar panels. On the right-hand side, one of the circles is missing. What happened, that was picture taken in 2010. What happened was that during winter, the snow, carbon dioxide snow that fell on this, on the solar panel, essentially broke the panel. It was so much snow. So that's something you have to consider when thinking about going to these regions. Next slide, please.
So Chris, one way to, Chris, yeah. A question. But that carbon dioxide snow doesn't go that far south on the latitudes, right? Right. How far south do we really find it? Would you remind me, because I don't remember that.
So we have another data point at 47 north, which is Viking 2, and you didn't see the significant layer of carbon dioxide snow. In fact, I've got a picture about it, and you have water ice. Frost, essentially, at the Viking, which is 47 north. So carbon dioxide snow is going to be probably 60 degrees and up. Okay, the Phoenix was 67.
Okay, got it. Thank you.
So going back to the slide, so one way to do this, is to put a greenhouse. You have this greenhouse that captures solar energy, or you can put nuclear energy inside, and you heat it up. You sublime water that's below the surface. The water is captured along the beams on the side, and it's recovered into a container. So it's relatively simple and passive way to do this. Next slide, please. Another way to do this is, let me just put the slide here. Another way to do this is to dig a well. You can essentially dig a well into subsurface ice, warm up this subsurface ice to create liquid water and pump it to the surface. This is actually called Rodriguez well, and it has been deployed in Antarctica and in Greenland to supply water for folks living there in Greenland and Antarctica. It's a relatively simple approach. You just may have to make a well, and you heat it up and you pump water. But the biggest problem is energy. How much energy you need to use to heat up this water and pump it out? It's actually a significant amount of water and a significant amount of energy. In fact, it gets worse when you go into cold temperatures. Cryogenic ice is a very, very good conductor of heat. It's 3 to 4 times conducts heat faster than than warm ice. So let's go to the next slide, please. Is this, by the way, is this slide projected on YouTube?
Yep.
Okay. Thank you. So what the way to look at this is we've done some work on melt probes for Europa and Mars, and if you think about it, the problem is very similar to melting through ice and penetrating down. When you do the math and you develop these equations for predicting how much energy you need to melt, what you get is an equation and the graph, resulting graph shown on the picture here. It's a log-log curve. On the y-axis, you have power required to melt and keep the borehole open. On the x-axis, you have melting speed in meters per hour. And then you have solid dotted lines towards the bottom. These are the straight lines. And you have these curvy lines towards the top. The solid lines indicate energy required to raise the temperature and melt at different temperatures. And then the solid lines on top it shows how much energy is required to keep the borehole open while you're penetrating at certain temperature and certain speed. So bottom line is you spend significantly 90% or more energy keeping the borehole open, preventing refreezing, than penetrating through ice. Okay, so conductive losses are significant. They're like 90+%. So if you do the math, saying, hey, I need 1 kilowatt-hour to melt a liter or 2 liters of water, well, you better multiply this number by 10, because this is how much energy you're actually going to need to keep the borehole open. Okay, this equations change if you have different borehole diameter or melt probe diameter and different length of the melt probe. This particular graph is done for a 1-inch diameter and 7.5-inch melt probe that we've been baselining for some of the work we're doing for Europa and Mars. Next slide, please. So let's look at the low latitudes where Curiosity is. Next one, please. So what Curiosity found, Curiosity has a drill and it has a scoop. So the scoop digged out some of the reddish dust that's everywhere on Mars and analyzed this reddish dust with a gas chromatograph and a spectrometer. What it found is that there's actually quite a bit of water, 1.5 to 3% of water locked in this reddish dust. And it's locked as hydrated minerals. So there are certain minerals, phyllosilicates and so on, that have water as part of the crystal structure. So you can't really get this water out by warming up to 0 C. You really have to put a bit of energy to break the hydrogen bonds and decouple them this water from a mineral. But it's feasible. Nice. If you go to the next slide, next slide, please. Nice thing about this is that this regolith or reddish dust is everywhere. It doesn't take big excavation system to dig it out. It doesn't take a lot of force to dig it out. You can you can pull it out, dump it into a big pot, heat it up. You have to heat it up to like 200 or 300 C, and capture evolved water, and move on to the next site and dig it out. There are some areas that have gypsum. Yeah, gypsum, if you think about it, has a lot of water. If you remove water, it becomes anhydrite, and then if you put water, it becomes gypsum. So if you ever broke your hand, and had to go to a hospital and get a cast, they take this dry powder that add water to soak it up into a paste, and then they put the paste around your leg or arm, and it sets. So that's a gypsum essentially that we have on the surface of Mars, and it still has plenty of water. Next slide, please.
Before we move on, we had a couple quick questions from the chat. Gitz Finch was wondering, I think it's basically wondering if you'll make these slides available to the teams.
Sure.
All right. So hopefully that answers your question yet. And then we had another question from Max Parks. I think it's going back to the boreholes. Could you pump water out of the borehole as it melts to prevent the hole from freezing again?
Yes, you have to do this, but inside the borehole, you have to have pressure above the triple point of water. So essentially, you have to pressurize it a little bit. So you have to seal it, and because you pressurize it, you're gonna be losing heat through gaseous conduction as well. And if you have you need some kind of a pond at the bottom of this cavity, of liquid water, and this pond has to stay warm somehow. And obviously there is one approach. You just keep on melting down and pumping water up. That you have to do the math. How much water you need, what's the diameter of the borehole you need, how deep you have to drill down or melt down to pump this water. You may find that probably the best thing to do is to melt down 10 feet or 20 feet and melt out big cavity, as opposed to have thin and a slim hole going deep down and they have the same volume, right? So you have to do the math and the thermal math as well.
All right, let's get back to these slides.
So the next area is middle of the road. So we talked about high latitudes, low latitudes. Now let's go to the mid latitudes. Next slide, please. This is actually a pretty exciting area. So the nice thing is it doesn't have carbon dioxide snow falling every winter. It has actually frost in winter. So the white stuff that you see in a picture, that's actually ice, water, snow, or frost during winter time. This is where Viking 2 landed. So Utopia Planitia. It's what we later on found, a few years ago, is that if Viking 2 could have dug a deeper trench, it would have hit water. Okay, so we were back in 70s, or I think it's 80s. We were very, very close to discovering water. Okay, if we could have dug another, a foot or so, it's amazing. We only discovered this now. So that's a relatively good location, because you get enough solar energy. You don't have to worry about the carbon dioxide snow, yet there is a water near subsurface. So how do we deal with that? Next slide, please. There are two problems, and problem number one is sublimation. Let's go to the next slide, please. As you all probably know by now, the atmosphere of Mars brackets triple point of water. Northern hemisphere from equator up, it's a low-lying area, so they have pressure which is above triple point of water. So you could have potentially liquid water which is sort of unstable. Southern hemisphere has highlands, which means the atmospheric pressure is lower, and the atmospheric pressure is actually below triple point of water. For reasons related to entry, descent, and landing, we've been going only to the northern hemisphere, which has lowlands, because you have more of the atmosphere to slow you down during entry, descent, and landing. In the southern hemisphere, you don't have a lot of atmosphere. So you cannot dump as much energy into atmosphere during landing. So all the missions actually went to the equator and up. Okay, that's something to keep in mind. Anyway, if you drill into or put a lot of energy into the ice at these conditions, what you're going to do, you see, is sublimation. Let's go to the next slide, please. So here, what it shows is a drilling into ice saturated rock. Okay, this piece of rock is a sandstone that's been saturated and frozen with water. And when you drill and your drilling system is not very efficient, so it puts a lot of heat, this heat turns into is taken up by ice as a latent heat. And ice turns into vapor, blows the cuttings out of the way, and this ice or water vapor is lost pretty much forever. From a drilling standpoint, it's nice because you have natural drilling fluid that blows the cuttings out of the way, but you're also losing vapor as you're penetrating down. And this is what this is part of my PhD and something that got me hooked onto ISRU and Mars exploration. Next slide, please. Next problem is the excavation of icy soil. Next slide, please. This graph shows strength in an unconfined compressive strength for MPa as a function of water content at cryogenic temperatures. That's something you guys have to keep in mind. Even if you have frozen soil at high enough water content and a low enough temperature, the soil is like essentially concrete or harder than concrete. So you need to think about how you're going to excavate this. Okay, this graph is a reason why Mars Phoenix, if you remember, had this drill bit. Okay, because we couldn't scoop it out with this sharp blade. Next slide, please.
I had one quick question. You talked about the water content in the soil acting as a natural kind of lubricant for the drill. Is there a percent of water content that you're looking for before you lose that effect, or at which point it kicks in?
Actually, it can kick in with relatively low water content, and the reason why is that water, solid water, as it turns into vapor, expands, million times in volume, and it doesn't take a lot of gas. Gas in vacuum or low pressure conditions is very powerful. It doesn't take a lot of gas to actually act as a very effective means or medium for cuttings removal. Just to give you idea, because we turned this into a ISRU sample, the pneumatic system that came out of this was turned into ISRU sample transfer system, which we have flown on a reduced gravity plane in vacuum, and with 1 gram of gas at 6 psi absolute. So that's not that's 6 psi above absolute vacuum. We managed to lift 6,000 grams of soil, okay, at very high speed. So 1 gram of gas at 6 psi absolute, which is half of atmospheric pressure, lifted 6,000 grams of soil. So you don't need a lot of gas to create this effect.
Wow, thank you.
Good question. So how do you deal with with this very strong soil? We looked at sort of what happens if we have relatively low water content and relatively high water content. So what we developed is a percussive scoop. If you think about it, when folks trying to break the concrete, they're using a jackhammer, right? So we thought, hey, how about sticking a scoop at the end of a jackhammer and trying to give it a go into the soil and see what happens. So this is a test fixture. We have a soil bin with a jackhammer at the back of a scoop, and this scoop was the size actually of a surveyor lander scoop that was deployed on the moon. Next slide, please. Can you click on both of these videos, please? So the video on the left-hand side shows if you don't percuss, you don't hammer, whereas on the right-hand side it shows hammering. Even if you're not geotechnical expert, you can see that there is a difference. Okay, there is a big difference, and the difference is how much soil is being displaced in front of a scoop on the left-hand side as opposed to right-hand side. On the left-hand side, the scoop is pushing essentially a huge volumes of soil, whereas on the right-hand side, the scoop is pushing small volumes of soil. And if you had the X-ray eyes, what you would see is the picture on top. The soil essentially shears through like a so-called shear zone. These are the imaginary lines, okay? If you do not percuss, if you do not vibrate, the scoop engages significantly larger volume of soil before it shears. Whereas if you're percussing, if you're vibrating, the soil, this imaginary wedge gets much shorter, and this volume of soil essentially tells you how much forces you need to excavate. Okay. So bottom line is, with percussive scoop, you can dig much faster with lower forces than with a static scoop. Next slide, please. And if you do the tests and you get graphs like this is on the y-axis we have mean excavation force, on the x-axis we have frequency of a percussive system. And here what you can see, the force drops if you have no percussion, no vibration. The force goes from 160 newtons initially down to like 80 newtons. If you start with percussion, like 250 newtons and 250 blows per minute. Then if you keep on going to like 750 blows per minute, the force drops to like 40 newtons and so on. This graph actually is important, okay? It's very important because it shows you how much force is being dropped and how much energy you have to put into the system to reduce the forces. The blows per minute of frequency is directly proportional to power. And if you look at the slope of a curve, you'll notice that if you go above 750, you have diminishing returns. If you go from 750 to 1,000 to 1,250 to 1,750, you're not dropping in a forces very much, but your power actually goes linearly up. So if you go from 750 to say 1,500, your force doesn't change, but your power doubles. Okay. So now you need to, as an engineer, you need to know that, okay, at 750, I've got the biggest bang for the buck. I'm gonna stop at that and put energy into the percussive system, and my forces will drop by a factor at least 4, okay? And that means that, the excavation rover can be 4 times smaller. That means that a spacecraft going to Mars can be 4 times smaller. That means a rocket launch being, that we use here on Earth to launch the spacecraft to Mars can be actually much smaller. So
Chris, so when you do an analysis like this, there are assumptions, correct, about the density of the soil that you're dealing with, which may or may not be applicable to Mars. Is that a true statement?
It's a true statement. We actually did tests with a medium density, high density, and low density soil. And if you have very loose soil, so that's a very good point. If you have extremely loose soil, you're not getting as much benefit, okay? But if you start with a loose soil and you're moving the scoop, you're compacting the soil. So at one point, this loose soil will become compact soil, and you're gonna start hitting some significant forces. So there is so we have a couple of papers on this, and the answer is not simple, but the state of density of soil has to be considered.
Okay, thank you.
Sure. Also, on top of this, the gravity has to be considered as well, and it's not as simple as 1 to 3 for Mars or 1 to 6 for the Moon. It's also a function of how big of a scoop you have. Okay, so there is more to it. Yeah. Next slide, please. Are we projecting the slide?
Yeah, we are.
Okay, great. So what we did, so we thought, okay, great. We know that percussive scoop works. So how about testing this percussive scoop in an icy soil? So we took the soil, we frozen it, so you can see the cooling coil going inside. It was frozen only at -20°C, and then again we give it a go. Next slide, please. And this shows the same scoop. As you can see, we have a high-tech videography with a data sheet. So here we have probably 1750 blows per minute at very high so it's relatively high frequency, relatively high joules per blow, and we're percussing down into the soil, and we're trying to move from right to left, or the bin, soil bin moves from left to right. And we stalled out. Essentially, we pushed with 3 kilonewtons of force while hitting with like around 4 or 5 joules per blow. That's pretty significant. And we stalled out. We couldn't penetrate this icy soil. So what we realized, we can't do it with percussive scoop. We have to do something else. Next slide, please. So then we looked at a hammering system, hammering drills. Next slide, please. We quickly took a Home Depot drill, and you can see actually the drill bit, and we drilled a hole in a matter of seconds. On the right-hand side, you have a scoop that got stuck. On the slightly to the left, you see this dirt on the surface. That's a hole created in literally a couple of seconds with a rotor percussive drill going into this icy soil. So we realized we're onto something. Next slide, please. And then we look back into our Arctic data. Okay, we spent weeks every summer doing drilling, excavation in the Arctic, and we looked back to determine how much energies we needed to drill into it. And all of a sudden, we realized there is a pattern when it comes to penetration rates, bit diameters, percussive energies, and things like that. Next slide. We also decided to develop more of this percussive technology and test it in Antarctica. Antarctica is actually pretty good Martian analog for a couple of reasons, and I'll talk about it in a couple of next slides. But it's a great trip to go down south. It takes a while to get there, but it's worth it. The analog environment and the geological uncertainty is all worth it. Next slide, please. So to get to Antarctica, you go to Christchurch in New Zealand on a commercial flight. Then you board an airplane like C-17 from Air National Guard, and you go on a couple of hour flight. You land on ice in McMurdo Station. So actually, I took this video. I ran down to ice to take this video, and this video ended up in a National Geographic as well. It was pretty fun. And then once you land, you take all your gear. Next slide, please. And you go to the McMurdo Station. You spend probably a week, 2 weeks to check everything out, to pack your bags for deployment. And on the bottom left-hand side, you see Scott's hut. This is, if you remember Scott and Amundsen trying to get to the South Pole. This is what Scott built and winter over while try getting ready for his expedition. So it's just across the across this short bay from where we've been putting everything together. Next slide, please. So we fly on a B-212 helicopters to get to the to dry valleys. Next slide. Next slide, please. Dry valleys is actually a very interesting location because it has this desert pavement, this what you see like a reddish rocks and soil overlaying ice and icy soil. So it's pretty much exactly what we've seen at the Viking landing site and what we've seen at the Phoenix landing site. And this location is high enough and cold enough that you do not get liquid water. All the ice that's being formed is formed from vapor. Vapor deposits itself in the ground, percolates down between the rocks, between the soil, and forms this very competent formation. Next slide. And this is what you see in the top right-hand side. It's a sort of cross section of this desert pavement. Again, dry, desiccated layer formed over ice cemented ground. And again, this ice cemented ground, we used picks, we used chisels. We couldn't get in, but the drill on the left-hand side next to our tent actually could manage to drill. Next slide. And we deployed it also in ice. With we managed to drill with 100 watts of power and very, very low energy. So percussive system actually works. Next slide. So question is, how do you combine percussive drill with with water extraction system? Next slide. We looked at the 3 different options. The first one we call sniffer. So it's a drill with it's a hollow drill with sort of perforations. An idea here is that you would drill down below the ground, you would heat it up, and you would hope that water vapor would go through these perforations up the drill tube and into the condenser. On the right-hand side, we have a deep fluted auger. So here idea is you drill down, say half a meter or meter down, you capture icy soil on the flutes, you pull it back into the sleeve, into a reactor, you heat it up, and then water sublimes and is being captured on the condenser as before. And on the right-hand side, you have a coring drill. What you see is a cross section. You drill down, you form this a core, you heat it up, and the water vapor goes through the perforations again, up the coring tube into sort of a sleeve and straight into the condenser. So these are the 3 potential options that we decided to test out. Next slide. Next slide. To do this, we set up an experimental setup. So you can see a vacuum chamber with our a cold finger or condenser with a closed loop cooling system, with the soil and vacuum pumps and data acquisition system and so on. Next slide. The first experiment was with a sniffer. On the left-hand side, you see the actual sniffer that was put in the soil, in the icy soil, and then you have a tubing going into the condenser on the right-hand side. Next slide. And the results were pretty disappointing. The problem was that something that actually we expected. If you think about basic fundamental ways the vapor travels to the cold fingers. Okay, vapor settles always where it's the coldest place. If you have a cold finger in the freezer, that's where water vapor condenses. Water vapor does not condense on a hot plate. And if you have a sniffer, which is hot, water vapor is gonna try to go away from a sniffer as opposed to into it. And that's exactly what we found. Water vapor was subliming away and blowing out of the hole and lost into the vacuum, as opposed to being attracted into this hollow tube, drill tube. So it didn't work. Next slide.
We do have one question. Yitz Finch again asks, is percussive energy significant compared to improved digging energy?
Percussive energy is going to be lower than digging energy. If it's something, the term is, so you really, so if you take the same icy soil and you have a drill and you have a percussive scoop, if you're referring to percussive scoop, firstly you can't get into it with percussive scoop. You're gonna end up essentially breaking the scoop, okay? And that means you're gonna be putting energy to sort of like crush the soil as opposed to break it, okay? So from this perspective, energy is gonna be higher. There is term called specific energy, which tells you how much energy is required to excavate cubic centimeter, cubic inch of soil. So that's a good term to use if you're trying to figure out how efficient is the system. But the percussive drill is pretty efficient, especially in a competent formations.
All right. Hopefully that answered your question, Yitz. Let's keep going.
So next, what we did is we looked at the auger system. So here you drill down, and the flutes are packed, essentially. They're fully packed with soil, icy soil. And idea was to heat up this auger and the sublime water away. Another generation of this fluted auger had these like pins going, 4 pins going right between the flutes. These we called heat spreaders. Try to dump heat, closer to the center of the soil sample. Next slide, please. And the results were actually pretty good. Okay, what you see on the left-hand side is a reactor. We managed to remove pretty much most of the water. What you see in the middle is a water in our container. On the right-hand side, you have dry soil. So pretty much all the water was gone. So pretty high efficiency. It worked really well. Next slide. And then we look at the coring system. Here you have, we use 1-inch coring into the soil. Similar setup as before. And we heated up sort of like a sleeve inside the coring system. Next slide, please. And the results were amazing. Okay, were absolutely amazing. We managed to essentially capture the vast majority of water, probably up to 90%, with relatively low energy efficiency or high energy efficiency at 1.7 watt-hour per gram. And what you see is actually quite a bit of water. So we realized out of all these free options, the coring system is actually from the water extraction standpoint is much better. Next slide. And this table essentially summarizes it. The energy efficiency for coring systems on average is like 2.2, for auger is 4.5, for sniffer is 36, and water recovery is on average 65% for coring system, 25% for auger, and sniffer is barely 1%. Okay, so we know which one is the winner. Next slide, please. From a drilling standpoint as well, if you think about a coring system, you only need to break this so-called a line required, or curve, or annular space required to form a core. Whereas for sniffer or auger, you need to cut this entire volume of the soil. And from this perspective, you're pumping a lot of energy into auger or sniffer, a lot of drilling energy, as opposed to the coring system. So from a drilling standpoint, coring is also much more beneficial. Next slide, please. So here, what we decided to do is develop this coring design. Right now we designed it to drill around 0.5 meter below the surface, capture a couple of inch diameter core, heat it up, and pump water to the cold trap above this. And we actually in the process of doing tests. Next slide, please. So here, what you see is our vacuum chamber with the cold plates on either side, with this entire drilling system and cooling coils and auger towards the bottom. and the soil sample right at the bottom, you can see like an opening. So we've done tests right now in ice, in rock, and we're moving into the soil. Right now we are qualifying the drilling system, trying to determine how much energy we require in different formations to penetrate down into a half a meter depth. And so far results are looking really good. We can penetrate down. The life of the system is actually pretty good, and we can penetrate icy soil, penetrate ice, and penetrate rock. Next slide, please. And this is one of the potential architectures. You have stuff like this on the Curiosity-sized rover. You would have MMRTGs. These are the nuclear reactors sitting at the back of the rover, providing a significant amount of heat. So each one of these nuclear reactors, which are plutonium-based, provides close to 2 kilowatts of heat and 100 watts of electrical power. So electrical power we would use to actually rotate, drill and penetrate below the surface, but we would pump the heat, the waste heat from this nuclear reactor to essentially to the soil. Right now on a Curiosity rover, some of this heat is used to keep all the electronics warm, is used to keep electronics warm, but a large fraction of this heat is essentially dumped into the atmosphere and lost. But if we have this excavation system, or extraction system, we can take advantage of this plutonium-based reactor to use the heat and be much more efficient this way. Next slide, please. And this is another potential architecture. We call it the walker or spider. It was initially designed for asteroid mission. That's why you have these water extraction reactors at a very steep angle on each footpath of a spider. They dig at the steep angle, they penetrate down, they capture soil. Water is extracted and pumped into the center of the spacecraft. So this could go on an asteroid. It could actually go on the moon as well. So instead of roving around, you can essentially walk. You can move these reactors and walk like a spider, and capture water this way, and generate resource. Next slide. So I'd like to conclude a couple of main points. Remember that ISRU is not just extracting things; it's about exploration first and then production second. And you have to think from a system level standpoint of view. Okay, as a system engineer, the entire system has to close with respect to the mass, power, energy, simplicity. The fact that you have something that can dig very efficiently doesn't mean it's the best approach. If you start considering implementation aspects and mass and power, you may find that some other approach actually would be better. Also remember, it's not just water out there. We have also salts and other potential contaminants that you have to take into account. And also, it's not just about water. We may find that some of these salts or some of the other things that we find in the water could potentially be a good resource. A water-rich soil at cryogenic temperatures is as strong as basalt. It's definitely stronger than concrete. Ice sublimes very quickly in vacuum. In hard vacuum at Martian conditions, because we are close to triple point of water, the things are getting better for us. Water essentially could be, you could potentially melt the water, but it's going to be very unstable. It's still going to sublime away. So you have to watch out for that and how much energy you put into it. The exploration can be done with a resource prospector-like roving system. This is something that we are developing for lunar exploration. But Lunar Resource Prospector, you can Google more about it. It's a really good platform that could be placed on the surface of Mars as an initial prospector to look for essentially hotspots, to determine how much water, how to excavate, and things like that. And then production can be done with the planetary volatiles extractor or spider, which are a couple of the last few slides are presented. Next slide, please. And all this work, has been funded by NASA. We're grateful for all the funding through SBIR, through HOMD Advanced Exploration Systems. NASA, SMD, so Science Mission Director, has a bunch of as well programs that funded all this development. So all the work that you've seen here is probably conglomeration of over a decade of technology development for this purpose. Next slide. And if you'd like more info, there are two really good resources. The first one is Space Resources Roundtable. This is an annual meeting dedicated solely to ISRU excavation, mining, and processing. It happens every year, and all the abstracts and presentation are posted on the Space Resources Roundtable website. So you can go back in time and see what technologies have been developed and their results. So most of the technologies are presented here actually are on this website as well. And another one is Earth and Space Conference. It's every 2 years. Next one happens in 2018, but you have probably over 100 papers in previous proceedings every 2 years dealing all about ISRU, excavation, mining, and things like that. So if you're looking for resources, probably these two would be your best bet. So with this, I would like to open the floor to the questions. And again, thanks very much, and it's been fun. Thank you.
All right, thank you very much, Chris. Do want to encourage anyone watching on YouTube to please get your questions in the live chat before we close out here. I did have one follow-up question for you, Chris. I was curious about with the coring method. You would acknowledge that there may be other materials in the water ice. So how do you deal with things that you don't want, and where do they end up going?
It's a good question. So you need to look at the filtration system, and we currently working with NASA Johnson Space Center. They're looking at different membranes. So if you ever camped out and then you had to take water from a stream and not worry about bacteria, you have all these ceramic filters and some other filtering systems. So we're looking at these kind of things to essentially filter out unwanted chemicals, and probably do some kind of, even we may have to do like osmosis or other processing. It comes down to, at the end of the day, it comes down to what the water is used for, how we going to extract it. And first aspect is we don't want to destroy all the plumbing that water vapor and everything is going through. We don't want to corrode this thing and having to throw it out after 6 months or a year. Another aspect is what we're using water for. If it's used for drinking, for agriculture and so on, it's a different ballgame. If it's used as a fuel, that's also a different ballgame. So you have to choose your battles. Each of those has to be tackled slightly differently because it's a cost-benefit analysis here.
So, Chris, I've got a question for you. Can you talk a little bit about if you do a Rodriguez well, which I think is the term, structure you need over top of the well to make sure it doesn't collapse on itself?
Right. So if you're cutting through the soil, you have to put some kind of a casing. You have to case the hole to prevent soil essentially plummeting down. Once you're in more competent structure, which is ice, you don't need to worry about it. But you need to make sure that if the pressure inside a Rod well or Rodriguez well is above triple point of water, which is required to form liquid water. And at that point, if you start melting water, your melt probe really has to be in contact with ice. So you need some kind of a deployment system that would keep on sort of pushing your heater against ice and be in constant contact with ice or liquid water. If you don't do this, the thermal conductivity of low pressure atmosphere is really, really bad, okay? You rely on gaseous conduction to transfer the heat into surrounding ice and melt it this way. So you're gonna be waiting a long time before you start melting, okay?
And one maybe other question, since we don't have any others, and if anyone does have any questions, we really would love to get them, because this is the goal here is to meet your needs and to help you prep more. But the thing I would ask is, what about, on Mars, we really don't know if there's biologies in the water. What do you worry about from a drilling standpoint, if anything, about potential biologies?
That's a good question. It's actually a very, very good question. Before we go there, everywhere you go where there is water, this is called Martian special regions for the purpose of planetary protection. NASA has a planetary protection office, and if you go to Mars, or if you go to areas that have possibility of sustaining some kind of life, you have to get a rubber stamp for your mission. For Mars, that means all the parts of a spacecraft going below the surface, touching ice, have to go through dry heat microbial reduction. So they have to be cooked at 125 C for something like 36 hours. And that means all the potential microbes and spores have to be baked out and killed. And once you do this, then you're gonna get green light to go and poke a hole on Mars and try to extract water, even if your goal is not life detection, it's water extraction. But you don't want to put some kind of organisms downhole in water and start a colony on Mars. Okay.
Okay, thank you.
Sure.
Did have one question just come in from YouTube from Harold Tab. What are your thoughts on the idea of evaporating the ice once it is reached and condensing it at the location of storage?
Could you repeat the question?
Sure. What are your thoughts on the idea of evaporating the ice once it is reached and then condensing it at the location of storage?
I assume this is for Rodriguez as well. You have to do, again, cost-benefit analysis here. The energy required to sublime ice or vaporize ice as opposed to melt it is significantly higher. Okay, so changing, relaxing the bonds as you go from ice to liquid is not as energy intensive as breaking the bonds to form vapor. You need to figure it out whether it's worth it. In my opinion, I would potentially pump water to the surface, keep it in a tank, and then decide what I want to do with this water. Whether I want to filter it out or for one application, or whether I want to sublime it and send it through a electrolysis system to break it down into hydrogen or oxygen for fuel production. Okay, so again, it comes down to a systems engineering here.
All right. Well, unless there are any last-minute questions, I think we'll turn things over to Stacy to close us out. Stacy?
Awesome. Well, that does wrap up our presentation for today. And we'd like to thank Rick and Bob for your continual phenomenal support of this program and for the support of the pre-briefings. Dr. Zacny, it's always a pleasure to have you share your expertise with us. So thank you for that very relevant and informative presentation. It was fantastic. A recording of today's Hangout pre-brief will be made available on our resources page of the Mars Ice Challenge website, in addition to the slides that Dr. Chris Zacny presented today. So in a few days, take a peek at that resources page and you'll have that information there for you. Line is 11:59 p.m. Eastern Time on November the 16th. And that form does close down at exactly midnight. So please make sure that you allow yourself enough time to get in and submit your proposal. We are so excited and really looking forward to seeing what type of innovative concepts that you come up with for us. So thank you for joining today and have a great week, everyone.
Thank you, guys.